So can everybody hear okay? Good. Okay, it's a real pleasure to be here today. The subject of black holes is really one of the most exciting areas of research right now, both in physics and in astrophysics. Physicists are very interested in black holes because of what they might teach us about fundamental physics that we still don't understand, and astronomers are very interested in black holes because it turns out that black holes are responsible for a wide variety of extremely interesting and exotic phenomena that we see in the universe. And so really what I hope to be able to do today is to convey some of that enthusiasm and excitement to you. As Steve mentioned, my own approach to these problems is theoretical, meaning that I don't go to telescopes, I don't actually do any observational work. In fact, when I first came to teach at Berkeley, I'd never been to a telescope before at all. So before I started teaching my first semester, I went with one of my colleagues to Lick Observatory, which is nearby, just to have the experience of being at a telescope. So as I said, what I'll hope to do is convey to you this excitement of both the physics and astrophysics of black holes. This is some of the material that we'll talk about is sometimes a little bit hard to get your mind around, so I encourage you to ask questions as I go. If you have them, I'd rather have you not be confused during the talk, only to have it sorted out later. So feel free to ask questions as we go. It may be if there's a number of questions and I want to kind of get to the end, I may ask at some point to hold off the questions, but I really do encourage you to try to ask them as I go. One of the things that's really great about the topic of black holes is not only is it an area that has tremendous excitement for practicing scientists, but it's also an area where the topic of black holes has really made it into popular culture. And there's a lot of examples of this. I'll just pick a few. This is before my time. This is a 1979 Disney movie called Black Hole, about this kind of classic, cheesy, old science fiction, a ship that's stuck orbiting around the black hole with the robot, going like this. There was a more recent movie which played on black holes called Event Horizon, which was actually a horrible horror movie. It's something about time warping, causing crazy people, and all kinds of problems on a spaceship. This is actually my favorite. So this I found like 5 years ago. Just, you type black holes into Google, and you get back a huge list of things. And one of them turns out to be a comic series about these kids in Seattle in the 1970s who were subjected to some horrible plague that makes them into ham sandwich-eating zombies. I've really yet to figure out what this has to do with black holes, but it's a wonderful indication of how black holes have made it into popular culture. To really drive this home, last night I went and looked up Google, typed in black hole into Google, came back with 36,600,000 hits. For those who are Google aficionados, if you put it in quotes, you still get, which gives you the phrase black hole, you still get 16 million hits. So there's tons of interest in black holes. A lot of this is actually really good. So if you type in black hole, the first 3 things that come back are actually really good educational sites about black holes. As you go further down the list, some of them are not so good. There's actually some misinformation out there, but this is a good place to start. My favorite actually is that prices are slashed today only on your own personal black hole from a nutrition company, no less. This is probably some very sophisticated form of liposuction. So this really is just another indication of how the extent to which black holes have made it into popular culture. My personal favorite example, though, is that the man whose fundamental theories are the basis of our modern understanding of black holes, which is Albert Einstein, has really made it into the absolute pantheon of popular culture, along with Barbie and G.I. Joe, and that Albert Einstein now has his very own action figure. If you think I'm making this up, it's actually sitting on my office outside my door I have the Albert Einstein action figure. And so, and there's some great suggested role-playing, which you can see if you go to the website. So these are just, some examples of the extent to which black holes have permeated popular culture. And I think that's a really great thing because it creates tremendous excitement about the subject. And so really what I want to do is just convey to you why it is that from the scientific perspective we're so excited about black holes, what's so interesting about them, why both physicists and astronomers are excited. And I'm going to do this really by trying to address two different questions. The first of these questions is to try to explain what do we mean by black holes, what really is a black hole. And you can think of this as trying to give you the perspective of a physicist on what black holes are. It turns out that physicists are extremely creative and come up with a lot of ideas that, so far as we know, have nothing to do with reality. Black holes are not one of those situations. So not only are black holes this great theoretical idea, first came up with actually in the late 1700s, as I'll talk about, but they actually exist in nature and give rise to a wide variety of observational phenomena that we see. And so really that's the second part of the story that I want to tell you. And there really are two different stories. When the original work was being done by physicists on black holes, there really wasn't much of a sense that these objects would turn out to be as important as they have been in astronomy. And so it's a great marriage of both physics and astronomy, this story about black holes. And so rather than jumping straight into black holes, actually where I want to start is with something a little bit simpler, which is a star like our sun. This is a beautiful image of the surface of the sun. And the story of black holes is really a story about the force of gravity. The force of gravity, as you all know, is the force that's keeping us here on the surface of the Earth. It's what holds us down to the surface of the Earth. But it's also the basic force in nature that holds together almost all objects that we know about in astronomy are held together by the force of gravity. Stars, planets, galaxies that we'll talk about later, these are all objects that are really held together by the force of gravity. And so, in fact, when you start to think about it for a little bit, the question that naturally comes up, which is that if gravity is trying to hold everything together, to pull us down towards the center of the Earth, to pull the surface layers of the sun down towards the center of the sun, then for the sun or the Earth or a galaxy not to just fall in on itself, there has to be something else pushing back out. Otherwise, gravity is this relentless force pulling in towards the center of an object, and there has to be something else pushing back out. And in the case of the sun, that something else is that the sun is made, it's a gas, like the room here, but it's much hotter. And the very hot gas in the center of the sun and in the outer layers of the sun pushes back out and actually balances the downward force of gravity. And the way it works is that energy is leaving the sun. We see light from the sun here on Earth. It's what keeps the surface of the Earth warm. And that energy is being constantly replenished by nuclear fusion at the center of the sun. So fusion keeps the center of the sun hot. That hot gas pushes back out and stops the sun from falling in on itself. And that process of pressure generated by fusion balancing gravity, that will last, it turns out, for about 10 billion years. Our sun is a little over 4.5 billion years old now. And so the sun is roughly a middle-aged star, but roughly 5 billion years from now, the sun will run out of hydrogen to fuse to heavier elements, and so something will have to change. The sun will no longer have this happy balance between gravity and pressure. And that fact is actually central to the story of how black holes come to exist in the universe. Okay. So another thing, yep, go ahead. What keeps the Earth from imploding is that the Earth actually has a solid crust, and so the intermolecular forces of the solid keep it from imploding. And not only that, actually, when you go in the interior of the sun, it's actually a liquid. So it's really more like the center of the Earth is a hot liquid, which in some ways is more like the sun than the crust of the Earth. And there it's, again, the high pressure of that liquid, which balances gravity. Good question. Okay. One thing we know about from both the sun and from our experiences here on Earth is that this balance between pressure and gravity is not absolute in the case of the sun or in the case of the planets. If I take this ball here and I throw it up, this is my fancy prop. I throw it up a little bit, it comes back down, throw it a little faster, it goes higher up. In principle, if I could throw this ball fast enough, I could actually cause this ball to escape the gravitational confines of the Earth. And that's illustrated schematically here. The ball that's not thrown up very fast comes back, a little faster, goes up higher, comes back. Throw it fast enough, and the object can actually escape the gravitational clutches. We're familiar with this from the fact that we can send rockets. We create big boosters of fuel that launch rockets up into space, that launch satellites into orbit around the Earth, or in some cases, actually satellites very, very far away from Earth in the outer part of the solar system. Astronomers have given, and physicists have given, a fancy name to this idea that if we throw something fast enough, we can escape the gravitational confines of an object. It's called the escape speed, the escape velocity. For the Earth, it turns out to be pretty fast, nothing that I can actually throw. I'd have to throw this ball 27,000 miles an hour to escape the gravitational clutches of the Earth. That's about 11 kilometers a second. But how fast you have to throw something to escape its gravitational clutches depends on how strong gravity is in that object. The more massive something is, the stronger its gravity. And the smaller something is, the stronger its gravity. So the sun is actually physically larger than the Earth by about a factor of 100 or so, but it's also almost 1 million times more massive. And so the gravitational clutches of the sun are actually much stronger than the gravitational clutches of the Earth. You're familiar with this general idea from seeing astronauts walking on the surface of the moon, right? Remember, when you see astronauts walking on the surface of the moon, it's almost like this slow motion. They take these very long steps, and that's because the gravity of the moon is weaker than the gravity of the Earth. So the fancy way of saying that, if you want to impress people in a bar, you can say you're a theoretical astrophysicist and you know that the escape speed from the surface of the moon is less than that of the Earth, while the escape speed from the sun is in fact much larger than that of the Earth, about 1.4 million miles an hour. So the rockets that leave the surface of the Earth, aside from the fact that they would burn up on the surface of the sun, if that weren't an issue, they would actually just crash right back down on the surface of the sun, because the sun's gravity is so much stronger. And this bit of physics, this really is the key bit of physics still behind our understanding of how it is that black holes come to be. This is physics that goes back to Newton. So soon after the revolution in physics and astronomy started by Galileo and Copernicus that we're celebrating with the International Year of Astronomy, Newton kind of codified our understanding of gravity, and this bit of physics was known in the late 1600s. The other bit of physics that was known at about the same time, which turns out to be crucial to the story of black holes, is that light, which is how the information from the sun travels to us, how information from the laser pointer gets to the screen is by light. Light actually also has a finite speed. It's very fast. So when I press this laser pointer, okay, and I shine it against the wall, you can't really tell, but it takes it about 10 billionths of a second for the light to get from the tip of the laser pointer to the wall. That's extraordinarily fast because light travels at about 1 billion miles an hour, 300 1,000 kilometers a second. So that is enormously fast compared to the kinds of escape speeds we're talking about, hundreds of thousands, millions of miles an hour. But there is a finite speed to how fast light travels. And this was also known in the 1700s, for example, from experiments watching the moons of Jupiter. We were able to deduce the fact that light has a finite speed. And this led two scientists, Jean Michel and Pierre Laplace. Michel did a lot of work also on earthquakes. Laplace is a very, very famous French mathematician. It led them to ask a really, really brilliant question. Most of doing research in science is not about solving the problem. Most of the time, it's about coming up with the right question to ask. And so they came up with one of these questions that we all wish we could come up with as part of our research. And the question they asked was basically combining this idea that light has a finite speed with the idea of the escape speed from an object. They said, what would happen if I had an object whose gravity was so enormously strong that the escape speed from that object, the speed needed to escape the gravitational clutches of that object, was bigger than the speed of light. And what they speculated is that this would lead to a star that couldn't be seen. Even if the surface of that object was producing light, the gravity of the object would be so strong that light would not be able to escape the surface of the object. And they called these very reasonable names dark stars. Stars we would not be able to see because light would not be able to escape the gravitational clutches of the object. And they actually went one better. They actually calculated how big such an object would have to be. Okay, they combined their knowledge of the speed of light with their knowledge of how fast something has to go to escape the gravitational clutches of an object, which depends on how much it weighs and how physically large it is. They combined those two ideas to calculate the size of a dark star. And what they found is that anything, in principle, could become a dark star, which is the early name for what we now call black holes, if I took a mass equivalent to that of the Earth and scrunched it down into a size about the size of this racquetball, that would become a black hole, a dark star, an object from which not even light could escape. Now, because the sun is much more massive than the Earth, I would only need, in parentheses, I would only need to collapse the sun down to about the size of Berkeley, a few miles big, in order for the sun to become a dark star or a black hole. And this is still the key idea to understand when thinking about what black holes are. They are objects so compact, whose gravity is so strong, that nothing, even traveling at the speed of light, which is the fastest speed that anything can travel according to the laws of physics as we understand them now, that an object can become so small that not even light can escape the gravitational clutches of that. And this was reasoned out in the late 1700s. Yes, go ahead. Outstanding question. That's just where I'm going. So you're absolutely right. So the reason, in fact, that this stagnated for 100 years or more, why there wasn't really any work on this idea, is that Laplace and Michel, in coming up with this idea, were using a wrong theory of light and a wrong theory of gravity. The theory of light they were using was actually Newton's theory of light, which treated light as a particle with a mass, just like everything else. And so they applied Newton's theory of gravity to light, even though that really isn't a valid thing to do, given the more sophisticated understanding of light as a wave that came along soon after. Okay, so you're absolutely right. The theory of light that they were using wasn't really the right theory of light. But not only that, it turns out that Newton's theory of gravity, which is the theory of gravity that they were using to come up with this idea, that also wasn't really right. Newton's theory of gravity doesn't apply when things are moving at nearly the speed of light. It only applies to things moving quite a bit less than the speed of light. And so what was needed to really come up with a physically consistent idea of this dark star black hole was a more modern understanding of both light and gravity, and that required the development of Einstein's theory of general relativity, which happened in the early 1900s. And so that's precisely why there really wasn't a lot of work done on this idea of black holes from the late 1700s, when the idea was first come up with, until the early 1900s. What was required in particular was a theory of gravity that applied to anything in the universe, whether or not it is a particle with mass or whether or not it's a wave like light. And that theory of gravity that applies to anything with energy, which both light and particles have, that theory of gravity is Einstein's theory of general relativity. Einstein's theory of general relativity took him about a decade to develop, from 1905 to 1915. The equations are famously mathematically complex. You're seeing part of them written on the board here. And general relativity is an interesting example where the equations are so mathematically complicated that it actually took physicists a long time to really understand what the math meant. And so in 1916, soon after Einstein's development of general relativity, Carl Schwarzschild wrote down the math that describes our modern understanding of black holes. He wrote down basically what is the gravity of an object in general relativity, and under what circumstances can nothing escape the gravitational clutches of that object. But it required this further development in our understanding of gravity and light and mass and energy to have a modern understanding of black holes. And the interesting fact is that even though the math was written down in 1916, 1915, it really wasn't until the 1960s that all of that math was understood. The term black hole was coined in 1967 by John Wheeler. Before that, these objects that we now call black holes were known as frozen stars, similar to the Michel and Laplace dark stars. And that difference in name, frozen stars, black holes, actually has something to do with the complications of the math of general relativity. Now, I can come back to that in the question period afterwards if people are interested. Okay, so I'm not going to go into any of the math of general relativity. I do want to quickly tell you what is the same in our modern understanding of black holes relative to what I just told you, and what is different in general relativity. This still is the basic idea of black holes in general relativity. A black hole is an object that is small enough that gravity wins out over all other forces in the universe. Gravity wins out over any possible kind of pressure pushing out. And so gravity reigns supreme, the object collapses in on itself, and nothing, even traveling at the speed of light, can escape the gravitational clutches of that object. So this is actually very similar to the Michel and Laplace notion of black holes. There are even more similarities than that. What we now call the radius of a black hole, and I'll explain why I put that in quotes in a second, is called the event horizon, the point of no return. And in our modern understanding of black holes, at least black holes that don't spin, that are just sitting still, the radius of a black hole that has a mass of the Earth is exactly what Michel and Laplace calculated, 1 inch. And the radius of a black hole with the mass of the Sun is exactly what Michel and Laplace calculated, a couple of models. So they got the radius right, What they got wrong is what the radius meant. Okay? In general relativity, what we mean by the radius of a black hole is simply the point of no return. The event horizon, the radius of a black hole, is the place inside of which nothing can get out. So if you're inside the event horizon, you cannot, in principle, get out to infinity. If you're outside the event horizon, you can, in principle, get out to infinity. And so what we mean by the radius of a black hole really has a lot to do with how information travels, how two different places can communicate with each other. And to kind of drive that home, the amazing thing about black holes that's very different from what we mean by the radius of the Earth, which is the solid to gas transition, or the radius of the sun. For both the Earth and the sun, when we talk about the radius of the object, there's actually something there. There's matter there. There's gas, hydrogen, iron, rocks, whatever. There's stuff there. There's nothing at the event horizon of a black hole. Gravity wins over all other forces, and so in black holes, all of the matter is sucked into the very center. And this point where everything is sucked into is called the singularity, which really means we have no idea what happens there. That's the truth, okay? In particular, general relativity predicts its own demise. General relativity says, look, all of the matter is sucked all the way into the center. Things get so dense, so hot, gravity gets so strong that the laws of physics, as we understand them, break down. What we need to understand what happens at the center of a black hole is a theory that combines the theory of big, strong gravity objects with the theory of the very small, which is quantum mechanics. So we need a theory that combines general relativity and quantum mechanics to understand the fate of matter at the very center of a black hole. We don't have this theory. This theory is generally called quantum gravity because it combines quantum mechanics and general relativity. One example that you've probably heard of is string theory. String theory is an example of an idea, a possible theory for combining quantum mechanics and general relativity, but we don't actually know yet whether it's the right one or whether there's some other theory. Yes? Right. So good question. So the first question is there actually something important about this location? And this is actually what led to the complications in understanding the math associated with black holes, was precisely the question of what really happens at that place. And I think the best answer is the following. If you were to take a person and throw them into a big enough black hole, okay, as they fell through the event horizon, they wouldn't really notice anything that dramatic happen. They'd notice that things on the sky started to look different because suddenly light couldn't get to them from the sky, but they wouldn't feel anything funny happen to them. Now, let me contrast that. If I were to throw a person into a black hole the mass of our sun, you would actually be completely ripped apart well before you got to the event horizon. So small black holes, the gravity is strong enough that it rips you apart before you hit the event horizon. Big black holes, it's not. And so falling into a big black hole, actually, the event horizon isn't all that special. And so that's why the really special place where things change, where general relativity fails, is at the center, not at the event horizon. Yep. That's a great question. So the other place in physics where we know that our modern understanding breaks down is in the very early universe. The universe is expanding. If we extrapolate that back, everything was incredibly dense, incredibly hot. Gravity was incredibly strong in the very, very, very early phases of the universe. And it's a similar situation to what happens at the black hole. I think there is very much a similarity in that we need the same type of physics to understand both phenomena. And that's why physicists are so excited. If we could understand the singularity at the center of a black hole or at the beginning of the Big Bang, that would teach us a lot about fundamental physics. They are different in that they're not exactly the same. So the universe itself is not simply the singularity at the center of a black hole. They're the same in that the physics breaks down in a similar way, but they're different in other important. Great question. Is there another? Yep. If I have three black holes and they're not near each other, they just orbit around each other just like the planets orbit around the sun. If they collide, neat things happen. If the black holes collide, you get very strong changes in gravity, which we actually hope to detect in the next 5 to 10 years with very sophisticated telescopes built on the Earth using a technique called interferometry that I'll mention a little bit later. And so what would happen is the black holes would collide and eventually combine to form a new single black hole. Yep. So, great question. Can we determine the age of black holes? How do we know how they get started? We can't determine the age. From the kinds of things we can see observationally, we don't have enough information. We do have some idea of how they get started, and I'll come back to that in a few minutes. Let me hold off on this particular topic, because I know there's lots of questions about this, and I'll be happy to answer more at the end, but I do want to continue through. So please hold your questions and come back to them at the end on this topic in particular. Okay, so this then is the modern understanding of black holes. Very similar to this idea of dark stars in some ways, but very different in others, in that there's nothing at the radius of a black hole. Everything is pulled into the center. And it's this fact that everything, once it's inside the horizon, gets pulled into the center that leads to the single biggest misconception about black holes in popular culture. And that is that black holes are essentially a cosmic vacuum cleaner that are going to suck up everything around them. And that we, sitting here on Earth, have to stay up late at night worrying about whether we're going to get sucked into a black hole. And that is not true. So black holes are, I tried to emphasize this, you might see, are in fact not cosmic vacuum cleaners. Only if matter is already inside the horizon, which is really tiny, remember, a mile big or an inch big. Only if stuff is already in the horizon does it necessarily get pulled into the center. If matter is far away from the black hole, it just orbits around like it orbits anything else. So one way to emphasize this point is that if we took the sun and replaced it with a black hole that had the same mass as the sun, nothing in the solar system in terms of the orbits of the planets, the asteroids, any of that, moons of any objects in the solar system, none of those orbits would change. Because when you're far away from a black hole, Newton got the theory of gravity right. The theory of gravity far away from the black hole is the same as it is for any other object that has the same mass. And so, in fact, far away from a black hole, you don't get sucked into the black hole necessarily, for the same reason that the Earth doesn't get sucked into the sun. Yes, the force of gravity is pulling the Earth towards the sun, but what that causes is the sun to orbit, the Earth, get the heliocentric correct, causes the Earth to orbit around the sun. And similarly, if I have a star orbiting around the black hole, the star orbits around the black hole does not necessarily get sucked into the black hole. Only when you get close to the event horizon does the gravity of the black hole become very different from what Newton predicted. And that turns out to be very interesting astronomically for reasons I'll get to in a little bit. Okay. So this then kind of culminates the story I wanted to tell you about what black holes are, about how we understand them as physicists, the types of physics involved in understanding black holes. And what I want to do in the remainder of the time is to tell you about black holes from an astronomical perspective. Do they really exist in nature? How do we find them? How do they manifest themselves observationally? And this is a difficult problem. It turns out it's not as easy as just looking up at the sky and seeing a black hole on the sky. Most black holes that you see on the sky are regions where there isn't much light being produced or where there's dust and gas blocking light from getting to us. So actually finding black holes is a little bit more involved than this, but one of the great results in modern astrophysics, really from the 1960s to the present, has been the growing recognition of how common black holes are in the universe and what an important role they play in a wide variety of phenomena that we see. And that's what I want to tell you about. It helps a little bit to know the answer before I tell you how we got there, so you know where we're going. And there are really two types of black holes that we know about with confidence in astronomy. One of these are very big black holes, very massive objects that sit right at the very center of a galaxy. So this is a picture of a nearby galaxy. Right at the center of that galaxy is a very big, massive black hole. These big black holes at the centers of galaxies can weigh between 1 million to 1 billion times the mass of our sun. And exactly how they form is not very well understood. It's related to how the galaxy formed. This is actually one of the most active areas of research. And this is what I'm going to focus on in telling you the story about black holes. Yep. Yes, great question. The size, the event horizon of one of these black holes is maybe 100 times the size of the sun. So say the distance to Pluto. So quite small compared to a galaxy. The size of the black hole would be, at best, the size of our solar system. It's extraordinarily small relative to galaxies. Yep. As far as we know, the only thing we can say about the size of the singularity at the center of a black hole is that we know roughly, and only roughly, when our modern theories of gravity break down. And the usual number that people throw around for that is something called the Planck length, and it's 10 to the minus 33 centimeters. So 0 point, a huge number of zeros, 1 centimeter. So an extremely small length scale, small compared to anything you're used to, small compared to the size of an atom, anything. So it's an extraordinarily small length scale. That's our best guess. But that's very, very uncertain because we don't really understand this quantum theory of gravity. So the other place that we know about black holes, where they exist in the universe, is black holes that are not millions to billions of times the mass of our sun, but rather black holes that are comparable to the mass of our sun, maybe 10 times as big. And these black holes actually form from the death of stars. The sun, as I said, will undergo nuclear fusion for 10 billion years, and then it runs out of hydrogen. And what happens then is it will start to contract, because there's nothing to keep it hot, nothing to maintain pressure, balancing gravity. The sun will contract. It will actually not form a black hole. It will form something else called a white dwarf, supported by a really cool kind of quantum mechanical pressure that I'm not going to go into. That's really the subject of another talk. But massive stars, stars that are born much more massive than our sun, maybe 30 times the mass of our sun, at the end of their lives, they will simply collapse down and form a black hole. Gravity will win out over everything. There'll be no energy left from fusion, and the star will collapse to form a black hole. There are millions of these in our galaxy and in every galaxy. When you look at any image of any galaxy, it has millions of these black holes formed from every massive star, almost every massive star, that was formed in that galaxy. Yep. So, good question. Low-mass stars, stars with masses comparable to the sun, are much more common than big, massive black holes. Sorry, big, massive stars. So 1 solar mass stars are much more common than 30 solar mass stars. What that means is that these black holes, even though there are millions of them, they're actually relatively rare. There are 1 trillion stars in a galaxy, or 100 billion stars in a galaxy. So there's a lot of them, but they're rare. Yep. Exactly. This is the great thing about how stars change in time. They simultaneously, their center parts shrink and their outer parts expand. So you're absolutely right. The outer part of the sun will expand. It'll get certainly very close to the Earth, whether or not, it's not quite certain if it will envelop the Earth, but it'll get very hot on the surface of the Earth. At the same time, the center of the sun will contract, turning into this object called a white dwarf. So these black holes, there are millions of them in every galaxy. Most of them are hard to find because, well, they're black and they don't emit much light. But occasionally, they orbit close to another star, and as is illustrated in this schematic diagram, mass can get pulled off of the companion star, spiral into the black hole, produce a lot of X-rays, and so we see black holes in galaxies as sources of X-rays. And I'll talk more about this process in a little bit. What I'm going to focus on in terms of our understanding of black holes as astronomical objects, I'm really going to focus on these kinds of black holes, the big, massive black holes at the center of the galaxies, which are the ones where there's been the most dramatic progress in our understanding in the past 5 to 10 years. Yep. I'll come back to that in just a second. Good question. So I'm going to start by telling you about the galaxy that we're certainly the most familiar with, that we know the most about, which is our own galaxy, the Milky Way. This is an image, an actual image taken with an infrared telescope of the Milky Way. When you look up at the sky, especially if you're in the southern hemisphere, you can actually see this beautiful disk of stars. And that's because most of the stars in our galaxy reside in this pancake-like configuration, or this disk-like configuration. This is an image. This is a schematic diagram of what it looks like from the side and from the top. Okay, so most of the stars and most of the gas is in this disk-like component. But at the center of our galaxy, there's a spherical component of stars, which is typically called the bulge of a galaxy. So galaxies are basically disks or spheres. That's a reasonably good approximation to most galaxies. The sun, as is indicated here, and as Carl Sagan poetically said, right, we live out here on the outskirts of a relatively boring galaxy in a relatively boring solar system. So we're out here in the disk of the galaxy. The total mass, the total weight, the total mass of our galaxy is about 1 trillion times the mass of the sun. Almost all of that is not in the form of stars or gas or normal stuff that we know of. It's in the form of some other fundamental particle called what we call dark matter, material that produces gravity but not light. And that's really another story, but I wanted to mention that for completeness. For comparison, the stellar mass is about 10 times smaller. Most of the stars, as I said, are in this disk, and maybe 10% or so of the stars are in this spherical part. So that's the overview of our galaxy from the point of view of its shape and where are the stars. Now, the size is enormous. This is the tricky thing about astronomy, is getting an appreciation of the sense of scales. The size of our galaxy is about 100,000 light years big. For comparison, the size of our solar system is a mere hundredth of a light year. And the distance between stars is just about a light year. So the galaxy as a whole is, 1 million times or more bigger than our solar system. Now, in addition to all of this great stuff, stars and dark matter and gas, disks and bulges, everything like that, there is, in addition, a single 4 million solar mass. You probably know that number to 10% for reasons I'll show you in a second. Black hole right at the center of the galaxy. Right at the bulge, at the very center, is this 4 million solar mass black hole. And in addition to that, everywhere in this picture, you can't see them, but there are millions of these little black holes formed from stars. But what I'm going to focus on is that big black hole at the center of the galaxy. One comment, the black hole is at the center of the galaxy, but we are not orbiting around the black hole, okay? Even though it's at the center of the galaxy. What I mean by that is that most of the mass inside where the sun is, most of the mass inside this position is dark matter and stars. The dark matter and the stars produce the gravity that causes the solar system to orbit around every 200 million years. Okay? The gravity that's causing us to move around is not the gravity of the black hole, it's the gravity of the stars and the dark matter. So the black hole is at the center, but we're not really orbiting around it. Okay. So how do we know that there's a black hole at the center? Well, I'm going to show you by basically zooming in to the very center of the galaxy. So this is a picture of our galaxy on the scale of tens and hundreds of thousands of light years. This is now a picture of the very, very center of our galaxy, and the scale of this is about a light year. So bigger than our solar system, but not much, maybe 100 times bigger than our solar system. And everything you see in this picture is stars. The big, bright things are big, massive, very bright stars, maybe 30, maybe even 100 times the mass of our sun. The little faint things are lower mass stars. Now what we're going to do is we're going to zoom in one more time. We're going to zoom in right there. Doesn't look all that special. We're not zooming in around the big guy. We're zooming into some relatively uninteresting point right about there. And that turns out is basically the center of the galaxy. This is now a picture of the very center of our galaxy. There's a scale bar here, 10 light days, the distance light would travel in 10 days. Okay? That scale bar is about the size of our solar system. What this is now, this is a picture of stars at the very center of our galaxy. Every point here is a star. And what two groups have done, one led by Reinhard Genzel, a professor here at Berkeley and in Germany, and the other led by Andrea Ghez, who's a professor at UCLA, what they've done is what at first sounds like a pretty boring experiment. They've just taken that picture over and over and over and over again for 15 years. Now, if you did that in most parts of the galaxy, that's what you would see over and over and over again for 15 years. It wouldn't change much. Most astronomical objects don't move very much on times that we can easily measure. Their light doesn't change very much. And so most parts of the galaxy, taking this picture over and over again, wouldn't be all that interesting. But it's pretty interesting when you do it at the center of our galaxy. And so this movie will now go forward from 1992 to the present, showing the location of these stars as a function of time. And remember, this is real data. So the position of those stars illustrates the actual position where they are as a function of time. So you notice that they're definitely moving. The stars are moving. They're actually moving very fast, right? We know how far away the center of our galaxy is. We see how fast they're moving on the sky. We can figure out the true speed. And they're moving at a few % of the speed of light. up to 10 or 12 or 15,000 kilometers per second. A typical star at a typical place in our galaxy moves at a couple hundred kilometers a second. So the stars at the center of our galaxy are moving 100 times faster, 10,000, 15,000 kilometers a second. The other thing you'll notice is that they're not moving on straight lines. This is extremely important. Galileo taught us that the natural state of motion is to travel in a straight line. And what Newton told us is that things don't travel in straight lines when they're being pushed or pulled, or some force is acting on them, right? The reason this ball travels in this arc, okay, is because of the gravity of the Earth pulling on it. And so the fact that these stars are not traveling on straight lines tells us that something is causing the stars to move. Some force is acting on them. Yep. Right, so it takes the center of our galaxy, this is like 1,000 years. Yes. So it takes a while, absolutely. It takes a while for light to, between 1,000 and 10,000, for light to actually get to it. That's exactly right. So we can actually use the motion of these stars, their speed, and where they are, to figure out what's causing them to move the way they are. In particular, these stars are moving on very particular shapes. The shapes of the motions of the stars are what we call ellipses. They're exactly the same as the shape of the orbits of the planets around the sun. They are the shape of an orbit produced when one object at the very center is causing the stars, or in the case of the solar system, the planets, to move the way they do. So we can use very simple Newtonian gravity to use the motions of the stars to measure the mass of the object causing the stars to move the way they do. Just like we use the motion of the Earth or the motion of Jupiter around the sun to measure the mass of the sun. And what we find out is that right there, not surprisingly, at the X, is a single object weighing about 4 million times the mass of our sun. Now notice this is really remarkable because the region where we're measuring that there is 4 million masses is the size of our solar system. Our solar system has one sun. It weighs one solar mass. This is 4 million times as much material in a region no bigger than our solar system. And the only way that astronomers and physicists can think of to have so much mass in such a small region is to have it all in a single object, a black hole at the center of the galaxy. And this really is now the smoking gun, best case evidence for a black hole in astrophysics. And there's no, it's beyond any reasonable doubt. There's no viable physics alternative explanation for having this much mass in such a small region. Now, we can do this in other galaxies. It's not as beautiful, right? Our galaxy is nearby, so you can actually trace the motions of individual stars. But you can do similar observations to measure the masses of black holes in other galaxies. And by doing this, and this gets to one of the questions that was asked earlier, and what we find is that galaxies that are more massive, bigger galaxies, in particular, galaxies that have bigger spherical components, bigger bulges, not bigger disks, have bigger black holes. So that might sound kind of obvious, bigger galaxy, bigger black hole. But astronomers got really excited about this. This was a remarkable insight into how the black holes form and how the galaxy forms. If you want the number to better than a factor of 2, if you tell me the mass of this big bulge that's 10,000 light years big, I can tell you the mass of the black hole at the center of the galaxy. And the number is that the black hole is about 500 times less massive than the bulge. So bigger galaxies have bigger black holes. In particular, galaxies with bigger bulges have bigger black holes. The interesting thing related to the question that was asked, if I have a galaxy that has a big disk but no spherical component of stars, it does not appear to have a black hole. So the big black holes at the centers of galaxies are related to the big spherical component of stars. Yep? Great question. So how does the size of the black hole correlate to the age of the galaxy? Well, it turns out that these guys, the ones with bigger black holes and bigger bulges, those do turn out to be older. They formed their stars when the universe was younger. So the universe as a whole is like 13.7 billion years old. These big galaxies probably formed most of their stars maybe 10 billion years ago. These littler ones, the bulges, are actually still forming a lot of stars today. And so these are the older ones. The bigger ones are older. The smaller ones are younger and are still forming stars. So this is one way we can infer the presence of black holes by the motions of objects around black holes. But it turns out there's another equally important way for determining the presence of black holes. And that has to do with the very counterintuitive fact that black holes are actually the brightest sources of light that we know of in the universe. Think about that for a second. Black holes are defined to be objects from which no light can escape. So how do they produce the brightest sources of light in the universe? It turns out that gas falling into a black hole produces a tremendous amount of light. As the gas spirals into the black hole, it heats up, it gets extraordinarily hot, millions or billions of degrees Kelvin, and that extremely hot gas produces a tremendous amount of radiation. This process is called accretion, the process of gas spiraling into a black hole, lighting up and producing very bright sources of radiation. Yes? Right. So this right here, these are two pictures of the center of our galaxy. One of these is taken in the X-ray, one of these is taken in the infrared. Wavelength's a little bit longer than what the eye can see. Let's start with this one first. Everything except at the tip of the arrow, everything you see here is the same stars that we were looking at in this previous picture. This picture and this picture. These are stars at the center of the galaxy. What this is now, this is actually a movie that's a couple of hours long showing how the light is changing in time. So you'll notice two things. One is there's an overall kind of fuzziness and shaking of the image. That's actually due to the Earth's atmosphere. The Earth's atmosphere changes in time, which changes the quality of astronomical images. But in addition to that, at the tip of the arrow, and the tip of the arrow is the position of the black hole determined from the motion of stars. At that position, there is a source of infrared light that comes up and then disappears. Comes up, disappears. So it's as if, an analogy is, imagine that the sun suddenly brightened by a factor of 10 and then faded away. And then the next day, brightened by a factor of 10 and then faded away on about an hour time scale. Huge changes in the amount of light we're seeing. We also see the same thing in the X-ray. This is an X-ray image of the center of our galaxy. Okay? And at the tip of the arrow, which is the position of the black hole, there's a source of X-rays. Now, this actually turned out to be rather hard to find the black hole in the light it produces, because relative to other black holes, ours does not produce a lot of light. It's relatively wimpy in terms of the amount of light it produces. And that's why, for instance, in this other image, it didn't just jump out at us that there was a big booming source of light. So what we think theoretically is going on is illustrated in this numerical simulation here. This is a numerical calculation of a bunch of gas initially orbiting around a black hole. The red stuff is dense gas, the blue stuff is low-density gas. The black hole is located right here. What happens is that initially the gas is orbiting around, but there's friction between different layers, different parts of the gas. And the friction gets rid of the motion of the gas particles, just like if I take this laser pointer and put it along the ground, it comes to a rest by friction. So what happens if there's friction in gas is it causes the gas to heat up. Friction causes things to heat up, and it causes the gas to spiral in closer to the black hole. And this is the difference between the planets orbiting around the sun, where there isn't friction, and we just orbit around for billions of years, and gas orbiting around the black hole, where there is friction. And the gas spirals in, producing these bright sources of radiation. And what we think we're seeing, let me hold off on the questions till the end, because we're getting near the end. So what we think we're seeing when the light comes and goes here, what we think we're seeing is in this gas falling into the black hole, we think we're seeing something analogous to a flare on the surface of the sun. This is a real image of the surface of the sun as it flares, okay? The scale of the image, this is about the size of the Earth. This is about an hour and a half long. And the sun produces these bright bursts of radiation, okay? Solar flare. And we think something similar is happening in this disk spiraling into the black hole, and that's why there are these changes on about an hour time scale in how much light is produced. And the amazing thing is that an hour, 30 minutes to be more precise, 30 minutes is about the period, how long does it take gas to rotate around the black hole near the event horizon. So these bright flares from the black hole are the last gasp as the gas is spiraling through the event horizon. Analogous to a solar flare, but now produced by gas falling into the black hole. So I want to end by putting our galaxy, which I've told you about in some detail because it's our best case evidence for black holes in astrophysics, in the context of other galaxies that we know about in the universe. And this is a schematic diagram illustrating something that actually already came up in one of the questions, which is that if we were not inside our galaxy, we're not able to look at the center of our galaxy in exquisite detail, if instead we were in some other galaxy far away, looking at the center of our galaxy, we would not see evidence for a black hole. And the reason is that all the light produced by gas spiraling into the black hole is completely swamped by all of the stars. So from far away, our galaxy would really just show up as a galaxy that has a lot of stars, most of them in the disk, some of them in the spherical ball. And that turns out to be true for about 99% of galaxies. About 99% of galaxies are like this, that if you look at them, you don't actually see much evidence in terms of light produced by gas falling into the black hole. You don't see much evidence for a black hole, even though it's there, even though every galaxy has a black hole at its center. And now it turns out that about 1% of galaxies are the opposite. If you look at them from far away, you don't see the galaxy. All you see is light produced by gas spiraling into the black hole at the center of the galaxy. That gas spiraling into the black hole at the center of the galaxy produces more light than the hundreds of billions of stars in the galaxy as a whole. So from far away, it just looks like there's a bright source of light at the center of the galaxy. Most galaxies are like this, but occasionally they look like this. This phenomena is given the unimaginative name of active galactic nuclei. The center of the galaxy is active. It's producing this huge amount of light. These are two examples Let's look at this one first. This is two sets of images taken with the Hubble Space Telescope with older cameras, like your digital camera, on the Hubble Space Telescope. This is what we saw looking at this particular galaxy. All we saw was the big bright source of light at the center of the galaxy. And you see these spikes coming out. These are known as diffraction spikes. These are not really real. They're not the light produced by the object. They're a phenomena of optics. When you look at a bright point source of light, you see these diffraction spikes. This is what you see with the fanciest, newest camera that was put on the Hubble Space Telescope. Remember, one of the wonderful things about Hubble is that we can send up the space shuttle and put new instruments on the telescope to take bigger and better images of astronomical objects. And what you see when you block out the source of light at the center is that it's actually surrounded by fuzz, and the fuzz is the galaxy. So here, gas spiraling into the black hole at the center of the galaxy is producing more light than all of the stars in the galaxy, and the only way you can even see the galaxy is to block out the light of the accreting black hole. This is another example of the type of energy and radiation produced by black holes. This picture is on absolutely enormous scales. This is millions of light years across, bigger than a normal galaxy by a factor of 10 or 30. Right there, the little red point is a black hole at the center of the galaxy. One of the most counterintuitive things that happens when I have gas spiraling into the black hole is that some of it doesn't actually make it in. Right before it's about to fall through the event horizon, it gets shot away from the black hole at 99.99% the speed of light, travels all the way out in these beams, these linear features we call jets, and then eventually lights up when it slams into surrounding gas. In this case, that doesn't happen until it's way outside of the galaxy. So these are two ways that this gas spiraling into a black hole can manifest itself as this extraordinarily bright source of radiation. In the radio, we see these jets of material launched from near the black hole at nearly the speed of light. And in the optical, we see these incredibly bright sources that outshine the galaxy. Now again, remember, this is a pretty rare phenomenon. Most of the time, galaxies are like this. 1%, a tenth of a percent of the time, they're like this. They're these active nuclei. And why is there that difference? Well, this really is the active area of research right now. Why do we sometimes get this? This is when the black hole is actually growing, gaining mass, okay? Why is it that sometimes I have this, and sometimes I have our own galaxy, which is not producing very much light, even though there's a big black hole at the center? And we think this has to do with how the universe itself formed. This is a computer calculation of the formation of a galaxy like our own Milky Way. Everything you're seeing, all the bright sources, are little galaxies. This is a movie going forward in time until at the present we will end up at our own galaxy. And what you notice is that the way galaxies form in our modern understanding of the universe is that they form by colliding with other smaller things. The universe starts out smooth and uniform, little galaxies form, and then those little galaxies collide together to form bigger galaxies. That's the primary way that galaxies form in our modern theory of cosmology. And the question, this computer calculation is for dark matter only, no gas, no stars. So what happens if there's gas or stars? Well, it turns out that if I have collisions of galaxies with gas, something very interesting happens, as illustrated in this simulation. This now just shows the gas. the two galaxies are colliding with each other. They're initially nice spiral galaxies like our own. Most of the gas is very far away from the center of the galaxy, just like it is in our own. But when the two galaxies collide together, that huge distortion in the gravity of the galaxy drives gas to the center of the galaxy. As you can see in this simulation, the gas ends up in these dense knots at the centers of the galaxy. We think that this is how the bulge, the spherical parts of galaxies, form. These are some actual images with the Hubble Space Telescope of colliding galaxies. This is an image in the X-ray of two galaxies colliding, both of which have bright X-ray sources due to gas falling into black holes at their centers. So it's this process. Collisions of galaxies is how galaxies like our own build up. During those collisions, gas gets driven to the center. That huge amount of gas at the center of the galaxy is when the black hole at the center of the galaxy gains a lot of mass, producing these active galactic nuclei and building the massive black holes that we see around us in the universe. Okay, so I'll stop up there and just leave a few summary points and be happy to take any additional questions you have. Sure, go ahead. Right. So the singularity, remember, the singularity is the place at the center of the black hole where we think all the mass is pulled in. A normal singularity is hidden behind an event horizon. So we think it's there, but it's actually hard to get direct information that it's there because we can't get information from inside the event horizon. Right? The light can't come from inside the event horizon. A naked singularity is the idea that maybe you can have singularities not hidden by event horizon. And you could actually see the singularity itself. This is still very controversial. We don't know what the right answer is. It's very much a question at this point of basic physics, of trying to understand whether those naked singularities can exist. We're not at the point yet of being able to try to study astronomically whether or not they exist. We're still trying to understand from basic physics whether they can exist. One idea is that maybe if you have mergers, collisions of black holes, the gravity is so distorted that you could actually briefly have a naked singularity not hidden by an event horizon. Based on the best calculations to date, that does not seem to be true. The singularity is always hidden by an event horizon. So that's a good question. What changes about the gas around a black hole for more massive black holes? It does become heavier. There's more mass around the black hole in gas for bigger black holes. But actually, one of the interesting things about our theoretical understanding of how gas spirals into a black hole is that theory doesn't depend very sensitively on the mass of the black hole. So the physics of how the gas spirals in and how it lights up, producing radiation and jets and stuff like that, that is not very sensitive to the mass of the black hole. Even though there's more gas around, the kind of physics doesn't really care that there's more gas. Yeah? That's a very good question. Well, first of all, the differential gravity on the tip of your finger and the back of your finger would be so strong that it would rip your finger apart. It would be very uncomfortable. So as you took your finger and you tried to put it closer, the tip of your finger would get sucked in really fast, while the back end of your finger would be left behind. So, let's forget about that complication. if you had a really massive black hole, you could, in principle, kind of dangle yourself with a big jetpack right above, really strong jetpack, right above the horizon and try to see your hand go through the horizon. What's tricky, and this is what led to a lot of the confusion in understanding the physics of black holes, is that as your hand started to approach the horizon, the light, say you were shining light on your hand, the light that you're sending in, or the light, you have a laser pointer that you're pressing on as your hand goes to the horizon, that light would get dimmer and dimmer and dimmer, and the time between laser pulses would get longer and longer and longer. And so you would see your hand kind of come to a halt near the horizon, even though, in reality, your hand would be going through the horizon. It's a property of how information is communicated as you approach the event horizon that gives rise to this illusion that things are hanging up there and not falling in, even though in reality you could fall straight through the horizon, your hand could go through the horizon. And this was the origin of this confusion. This is why black holes were called frozen stars, because there was this idea that they wouldn't actually form, they would just kind of come to a halt as they were trying to form. That's actually just an illusion. That's what you see from far away. But in fact, all of the matter rushes in to the singularity, forms a black hole on a very short time scale. Good question. Great question. So we have the story that the way you get all this gas to the center of the galaxy to build up the bulge and to build up the black holes through collisions, but you need something there to start with to funnel the gas onto. And that could be one of these black holes formed from a massive star that collapsed at the end of its life. There are also more exotic ideas of how that you could form bigger black holes when the universe was young, more like 1 million times the mass of our sun, and then pile gas onto those. And which of those is right is a very active area of research. Why don't we, if people are interested in staying to ask additional questions, I'm more than happy to stay, but if you'd like to go, please feel free to go ahead and leave now.